protic acids and bases. Okay. Protic just means proton, right? So that's the type of acid and base we're talking about. Kind of like the Bronsted-Lowry, if you remember those definitions in general chemistry. But acids and bases are all over the place, right? Carbonic acid keeps the pH equilibrium in your body. I mean, you can't stop them. And vitamins, they're all weak acids. So understanding the equilibria and being able to predict how equilibria would be changed with acid-base reactions is a big deal. They're everywhere in the environment. Well, I already kind of mentioned protic. Protic just meant a lot of what? What's the acid? Donation of? Yeah, H+. Hey, Shelby, do you know this? What is H+ really doesn't exist in nature? They think how does a bare proton exist in water? It's not H+. Yeah, I remember that. This is a lot of, you just add H2O to it, and that's the same as H3O. You're supposed to call it what? High hydronium. Yeah, you guys remember. Good. You add an acid and a base with these protic acids, Javier, and you always get a what and what? Add any acid, protic acid, base, you'll always get what do you get? Add an acid and a base, you get, someone said the W, you get the water and a salt. And what's a salt? What's a salt, Eustacio? Give me an example of a salt. Besides sodium chloride. Potassium chloride, right? You just have to name a cation and an anion. That's all it is. Cation and anion, right? Calcium sulfate, I don't care. Any cation, any anion. It's a salt. A conjugate acid-base pair, Alyssa. What does this having to do with anything? Conjugate acid-base pair. What is that? Okay, an acid donates a hydrogen. It donates that hydrogen, so that hydrogen's lost. It's now converted into a base. So that now then it could go the other way. That base could grab a hydrogen and go to the acid. But we're not supposed to say acid and base. We're supposed to say it's conjugate acid and it's conjugate base. Right? For example, I don't know. Sochi, give me an acid, any acid. What's that? HCl. Oh, not that one. That was a different one. Yeah, just H, anything. She says HBr. Caroline, conjugate acid or conjugate base? HBr. It's the acid, so it's got to be the conjugate acid. What would be its conjugate base, Albert? Well, that's Br, but technically that's not right. It has to be Br with a minus sign. Bromide. It has to be bromide. Bromide. Okay, that'd be the conjugate base. Remember that game? So just rip off an H+, and you'll have the conjugate base. And they go back and forth. Okay. The conjugate base of HCl is what, Daisy? Chloride. Good. And this conjugate base is definitely what, Brad? All right. The trick to answering this is to know what HCl, I guess. Right? HCl is one on that list of strong acids. Right? Weak. He says weak. Does everybody agree? Yeah, most definitely. Right? Because HCl doesn't even exist. It all exists. 100% is H plus Cl minus. So this base, that chloride, that conjugate base, it is a conjugate base. All right? It is so weak, it can't grab that hydrogen and go back. It is so, so weak. It ain't going to happen. Okay? But technically speaking, it's a conjugate base. But it's extremely weak. Autoprotolysis of water. Brandy, what does that mean? Autoprotolysis. Autoprotolysis. Now there's protolysis and there's autoprotolysis. Protolysis is you're forcing it to happen. You're forcing water to, that's not a good example. Let's just stick to autoprotolysis. Autoprotolysis means it happens automatically. It's natural. You can't stop this from happening. What happens with liquid water? It evaporates. That's one thing, but that's not autoprotolysis. It's a good thing, good idea. It dissociates. Water decomposes. Water falls apart. That's called autoprotolysis. It happens all on its own, Jenny. Water falls apart to what and what? H plus and OH negative. Okay. You can write H3O if you'd like. Now, if you write H3O plus, this has to be two H2Os. Right? If you want to write H3O plus, this has to be two H2Os, goes to hydronium plus hydroxide. But I mean, I'm so lazy, I don't even write AQs on ions. I should write aqueous on every single ion, right? They're all solvated. But we...
And does the autoprotolysis also take into account the reformation?
Auto...
Or is it strictly the decomposition?
Autoprotolysis, you're, dang it, you are good. We should have a backwards arrow going. These are equilibria, right? So how would you write the K expression? The because it's a very good point, Brad. Destiny, how would you write the equilibrium expression for that reaction?
Product of the reactant.
Okay, so it would be what over what?
OH, an H over H2O.
OH and the H, so H and the OH all over?
H2O, yeah, one.
Ooh, 1, why?
Because it's a liquid.
It's a liquid. Okay. Whenever you see a subscript on an equilibrium constant, you have to write the reaction a particular way. They're going to put a little what? Have you seen this before? A K with a little W. Okay. And that KW, you have to write the reaction that way. And I think it has to be at 25 degrees Celsius or something. But what is that number? 1 times 10 to the negative 14? Or 1 times 10 to the positive 14? Do you expect a lot of product or a little bit of product? Very, 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 very little, right? A billionth of a billionth almost. So 1 times 10 to the negative 14. 1 times 10 to the negative 14 is our KW. Okay. pH. We've heard of pH, Jessica. What's it used for? Yeah. Used to indicate whether the solution's acidic or basic, or how acidic or how basic. Now there needs to be an equation for it though, Victoria. What equation is used to get pH? Oh, very good. Negative log of H plus. Okay. So you plug in the hydrogen ion concentration, take the negative log of it, and you'll get the pH. Now, if this is what pH is, what would be the equation for POH? Exactly. The negative log of OH. In fact, you can take the P of anything. You can take the PKW. That'd be the negative log of KW. It's just, they call it the P function. It just means take negative log. Okay. Without doing the math, we could, but let's see if you remember this. pH plus pOH actually is if we derive it, we're going to need this number. I don't know if it's a hint. I heard somebody mumble it. 14. Right? And we could derive it. We would have to start with this expression and take the negative log of both sides. You end up with negative log. So you take the log of it, then you push the plus minus button. That's just the p function, how it's derived. Px is negative log of x. That's just... P always means negative log. Okay. I think the negative sign is in there because they like, you're dealing with really dinky numbers and it makes things more manageable. Strengths of acids and bases. Okay. Marlena, in the world, are there more strong acids or more weak acids? There's a gazillion weak acids, right. How can you tell them apart, Angelica? How can you tell them apart? Is the hydrogen in the front? Well, whether it's a weak acid or a strong acid, you're going to have a hydrogen in the front. So that's not going to be your hint. There you go. Matt's right. There's how many strong acids? 6. Know those. Then anything else has to be a weak acid. Okay, well, there you go. Name and formulas of all the strong acids. Jose, what's one of them? Hydrochloric. Hydrochloric. Chloric. And that would be what formula, everybody? HCl. We need another one. Kevin. HBr. And its name is hydrobromic. I can just do quotes, right, and write bromic. Mariella. Perchloric. Okay. What's its formula? Good. HClO4. Zach. Sulfuric. And its formula is H2SO4. That's 4. We need a couple more. Monica. HI. Hydroiodic. Okay, in my view, the last one is the most dangerous one. What is that last one, Shelby? Nitric acid. Smith is all worried about nitric acid because you get it on your skin, it feels just like water. Rubbing it all over the place, and then you start burning a couple minutes later, and then it's too late, right? Well, you have red stuff all over the place, right? Okay. Calculating the pH in strong acid and strong base solutions. Okay, let's just pick one. I have 0.30 molar HBr. How would I get its pH, Javier? It's a strong acid. Okay, I'm going to need this. He got you halfway there, Eustacio. Now what do you do? It's a deceptively straightforward answer. Because I mean, the only reason why this works is because it's strong. What's the concentration of the hydrogen ion? Same as this. Because it's 100% dissociated. So the concentration of H plus is 0.3 molar. What's the concentration of bromide? 0.3 molar. Right? You don't care, but it's true, it is. So take the pH, just take the negative log of 0.3 and you have your answer. What if you had a strong base? 0.012 molar. Ooh, you need a strong base. Alyssa. Strong bases? NaOH. In fact, it's just which first row OHs. There you go. You pretty much nailed them all then. Those are the only ones you're going to see. It's just the exceptions to the hydroxide solubility rule. So it's all the group 1 hydroxides and calcium, strontium, barium hydroxide. But I think if you just remember group 1, that's going to cover everything. KOH. So if you want to get the pH, Sochi, of 0.012 molar KOH, what would you do? Oh, you could do that. 14 minus pH equals POH, right? She's rearranging, where'd it go? This guy. POH is 14 minus pH. That works, but we don't know what the pH is. Just take the negative log of 0.012 molar, right? That would be POH. I could write it right here. Right? Okay. You could also play around, if you wanted to, with this equation and plug in 0.012 for hydroxide, solve for H plus, and then take negative log. It seems like more work, but okay. Here's where the work is. Finding pH in weak acid and weak base solutions. So I scanned this from the back of the book, Appendix G, acid dissociation constants. So there's a bunch of these. It gives the name of the acids. It gives you their structure. It has this little blue guy. Can you see the little blue guy? Kind of shows where the acidic hydrogen is in the structure. It's kind of neat. And then it gives the pKa and the Ka. Okay. What's pKa? Albert, what's this pKa? The little p meant what? Little p meant negative log, right? So whatever Ka is, they took the negative log of this Ka and they got that column. Okay. So what we need to figure out is what's the pH of these weak acid solutions. We need to write a Ka reaction because they gave us the equilibrium constants. They call them Kas. A probably stands for acid dissociation constant. But you have to write the reaction the right way. So a Ka reaction. Christina, I want to just, in general, say that my acid is HA, right? And A can be anything, okay? If using HA, how would you write the reaction? What do you think it's going to look like? They want to call it the acid dissociation reaction. So HA would probably go on the reactant or product side. The reactant, yeah. Right? Here's our acid, and it has to fall apart into probably what and what? It's ions, which are going to be H plus and A minus. There it is. So how would you write the KAX? Wow. Yeah, how would you write? I'm just asking for the reaction. There it is. HA goes to H plus plus A minus. How do you find the pH of a solution of a weak acid? So I don't know. We need to make something up. Brad will say, oh, we don't need to make anything up. Here's a question. We have 0.1 molar acetic acid. And he's right on the very top of that list. That's why I picked him out. What could be a game plan to get the pH of 0.1 molar acetic acid? And you're given all this information. The structure won't really do you a whole lot of good, but that Ka might. Have any ideas?
You can't assume complete dissociation, right?
Yeah, you can't. Otherwise, yeah, you're right. So since it's partial, it's this equilibrium problem, we're going to do...
Find the inverse, the anti-log, use that to find
ice. We're going to be getting to that when we get to buffers. Right? So we need to do ice. In all these equilibrium problems, whether it's solubility, finding pH, it's an equilibrium situation. You just do ice. But we need to do ice of a reaction, Brandy. What reaction are we going to do ice for? Anybody help her? What are we going to do ice of? We need a reaction. Yeah. And why this one? Because we know what its equilibrium constant is. We know it's Ka. But you have to write the reaction this way, otherwise forget it. Nothing's going to work. So let's, we could write HA goes H plus plus A minus, but let's just write it out the way it's supposed to be. That acetic acid is going to go to, Jenny, what would you say? What and what?
Either or equilibrium errors also, right?
Yeah, we should probably go back. C2H3O2 and H plus. And what do I need on this acetate? I need a negative sign. Okay. It won't really affect the ice, but it'll look better if we have it. Okay. Do I put anything, Destiny, in the initial row? You sure? I have 0.1 molar acetic acid, which is HC2H3O2.
Okay, so it's fixed.
Yeah, it's initially, this is its concentration. So that is what we put in the 0.1. Do I have any of acetate or initial H plus? They just said, no, they didn't give you any information on that, so you have to put dashes. The change row, I'll put what under the acetic acid, Matt? What would make sense there? Yeah, here, would I put a positive X or a negative X? It's negative X. And that's why I guess, conceptually, I wrote this. And then Brad asked, isn't it at equilibrium? Yeah, it is. But they're saying initially you have 0.1 molar. So it's going to be going to products. And then then it'll be reaching back and forth and reach dynamic equilibrium. But here's where it's starting out. So negative X, right? Equilibrium 0.1 minus X, right? And on the product side, it would just be X's, X and X, X and X. So then I set up my equilibrium constant, Ka, would be what over what, Jessica? What would you put in there? X times X perfect. And let's see what that number was. Oh, nice. At least it's not 10 to the negative 3 or something. Oh, look at this one. You don't want to be doing that one. Can you read it? That is a 10 to the negative 3. That'd be a full quadratic. Ugh. 1.75 times 10 to the negative 5. Okay, so I have a small equilibrium constant. So that means I don't expect a lot of product. Remember this? So X's should be really, really, really small, because K is really, really, really small. It's product over reactants. So X is going to be really small. I can't do anything with the numerator, but I've got this extremely huge 0.1 minus a really dinky number. This is essentially just 0.1. So that means this is approximately X squared all over 0.1. Let's see. Times 0.1, take the square root. About 1.32 times 10 to the negative 3 is what I got. Okay. The question, though, is, Victoria, did you get that number? 1.32 times 10 to the negative 3? Yeah, so multiply it times 0.1 and then take the square root. Yeah? Okay. So 1.32 times 10 negative 3. If you're using the big honking calculator, use parentheses everywhere. It's all only advice I can really give you. So that's my x, but we want pH. Naya, we want pH. So how are you going to get the final answer here? Exactly. Plug the x into the negative log because the x is the hydrogen ion concentration, right? It is. That is the hydrogen ion concentration. So my pH will be the negative log of 1.32 times 10 to the negative 3. And you got what? 2.88. Okay. Sound good? How about some compounds? This is a tough question, Ashley. Let's see if we can figure it out, though. Give an example of a compound that when you add it to water, you would create a weak base solution. A compound where you add it to water and you would create a weak base solution. Now, let's back up a little bit. What would be an example of a weak base? Right? Because the strong bases we talked about. What would be an example of a weak base? What's that?
Calcium hydroxide.
Calcium hydroxide. Now that would be an example of a strong base. Yeah, because he's an exception to the solubility rule. Ooh, ammonia. That's a good one. How about another one? Now ammonia, yeah, ammonia. How about another one? What I'm thinking of is you look at, is this a weak acid or a strong acid? Weak. I see a base there. What base do I see when I'm looking at it? C2H3O2 minus. That's its what base? It's conjugate base. How can I get him in solution? That's all I need to do. How can I get him in solution? There's no such thing as a bottle of acetate. It's negative. That's like touching one terminal of a battery. It's not possible. Put a cation on it that will make it dissolve. Now, what cations can I put on anything and it will dissolve? Group 1. Pick one. Lithium. Lithium acetate. Li(C2H3O2). So you pick any weak acid, look at its conjugate base, and you get it just by taking off an H+, and then attach one of those alkali metals. And you will have a compound where you can take it off the shelf, put it in water, and you'll have a basic solution. Solutions of weak bases are, Marlena? Basic, yeah, because they're conjugate bases. Okay, so to best describe the equilibrium in Helica, what reaction should be written? I don't know if you can see the little subscripts, but there's your answer. KB, because B stands for base. Okay, so we need to figure out how to write a KB reaction. Okay, so again, if HA is my conjugate acid, well, how would I write my conjugate base, Jose? If HA is my general form of conjugate acid, what would be my conjugate base? Just rip off an H+, and you're left with A, but with a charge has to be a negative. There's my conjugate base. So a KB reaction needs to be written this way. That conjugate base, Kevin, is probably on the reactant or product side. The reactant. Okay. Has anyone seen this before? Plus H2O forms HA, right? To see how you get the HA? That A negative is going to rip off one of those H's on the water, and it's going to leave OH. There's our product base, all right, that we're used to seeing, OH minus. Okay. So, looks good so far. So Mariella, maybe you can see what's coming. I'm going to say you have 0.3 molar lithium acetate, and I want you to find the pH. So you're going to have to do ice for the K. Where's Marlene? You're going to have to do ice on its Kb reaction. Make sense so far? Okay. But you need the Kb to do this, right? Because we're going to set up products over reactants, do the whole ice thing, but you need the Kb. And if you look, it's nowhere to be found. I mean, you can look as hard as you want in this book. All you're going to find is this bloody table. Nowhere is there a table of Kb for acetic acid. All it gives you is, the acetic acid and its Ka. How do you get it? There, she saw it. Where did you see that? Is it coming up? Nope. You hear? She said Ka times Kb is equal to Kw. Right? So if we're looking for the Kb for acetic acid, we just have to plug in the Ka for acetic acid, right? So if you're looking for the Kb for acetic acid, look up the Ka for acetic acid and then use the equation to get it. And that's what they expect in every single book, right? Even on the internet, you can't Google. Maybe you could, but I don't know. It would be very easy. I doubt they'll have it. They expect you to calculate it. Okay. So how do you find the pH? Oh, we're good. Good example. How do you find the pH of a solution of a weak base? Well, here we go. We have 0.1 molar sodium acetate. Okay. Now first, Jesus, do you recognize that, right? This is a conjugate base, right? Okay. So we need to write, we have 0.1 molar sodium acetate. We want to find its pH. We need to write a Kb reaction. And then we'll do ice on it. So how do we write the Kb reaction for this? What would you write? Right? You could write this whole thing, but I think it'd be easiest to leave off the sodium. Otherwise, you can have little spectator ions. So just write this part. Plus what, everybody? Water. And really, we should put a little L on it because he never shows up in ice, right? It's going to form acetic acid and hydroxide. Okay? So, Zach, how do I start filling in this table then? Yeah, 0.1 under there. So just be comfortable with, if I have potassium fluoride, 0.3 molar, what's the concentration of my fluoride? Right? This is what I want you to get used to doing. 0.3. You don't look at, my brain does not look at what ion? The group 1s. It never does, because they're always spectator ions. So when I see this, I see 0.3 molar fluoride. I don't even blink about it, because those Ks, the group 1s never do anything. So that's why Zach put a 0.1 right there. Under water, nothing, right? There's nothing there initially. Negative X, 0.1, negative X. Right. Hopefully that's how you'd fill in your ice table. And then we need to write KB would be products over reactants. And you'd write what, Monica? Minus X. Okay, now we got to get a KB though. So hopefully it's going to be a dinky number, right? My KB would be KW all over KA. 1 times 10 to the negative 14 divided by, what was that number? Yeah, 1.75 times 10 to the negative 5. And then you can get your KB. Right? And then you finish the whole question. When you do finish this, and you get your X, Shelby, how are you going to get your final answer for pH? Right? When you get your X, that's the concentration of what? Oh, subtract from 14, right? Right? She's saying, get your X, that's the concentration of hydroxide, and she said subtract from 14, so that means she's taking the negative log of hydroxide to get POH, then she's subtracting it from 14. You see that? So that's what you can do. That's what I would do too.
Can't you also just take it straight from the 1.0 times
Yeah, oh yeah, yep. It seems like there's more plugging into the calculator though.
concentration?
That would work. Successive hydrolysis. This is the last thing. And all they're saying is if you have an acid like phosphoric, it's got a bunch of protons, right? How do you relate all the different Kas? Because one H goes off. They call that Ka1, the most acidic hydrogen. Then the second one comes off. They call it Ka2. The third one comes off, Ka3. So how do you relate them all? So let's go ahead and see if I can show you. This is the relation you're supposed to figure out how to use. And if I have H3PO4, my little n, my number of acidic hydrogens would be what? 3. Okay, so let's use the equations. So my Kw equals, first we have to do I equals 1, then we have to write another relation for I equals 2. It's my little counter. The little i's are the little counters. And I is going to go all the way up to 3. Okay. So when I equals 1, my Kw will be Ka, everybody? My little I is 1. So in the relationship, Ka1 times Kb, 3 plus 1 minus 1. 3. Okay. Now you write the relation for I equals 2. Ka2 times Kb, Kb2, right? 3 plus 1 minus 2. Last one, Ka3 times Kb1. Okay. So if you had phosphoric acid, let's just make sure we're all on the same page. How would you write a Ka2 reaction? Right? What would the Ka2 reaction look like for phosphoric acid? The Ka2. Right? So Ka1 would mess with phosphoric acid, H3PO4. Ka2 is going to be starting with H2PO4 minus. That would be that's where it would start. Right? Because you already lost one. Okay? This is the second acid dissociation constant. And that goes to H plus HPO4 with a negative 2. Okay, that's the game that they're playing. Okay, if you had to write it. I'm kind of jumping in just to make sure you see it. Okay.
And so how did you know, so what's the, what are you looking at to figure out that reaction?
Well, you're going to need it if they give you a question like one of these. It's not, you're not going to see it very often at all. Okay. And then there's a bunch of homework, but
So then just real quick, for Ka3 then, it would be like HPO4 negative 2?
oh, Ka3?
Yeah, as if you were doing the same
Yeah,
thing.
so Ka3, exactly, you'd have to start with the HPO4 negative 2.
Okay.
And that would go to H plus PO4 negative 3. Yep,
Oh, so it's just
exactly.
hydrogen being moved each one?
Yep, successively.